Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. This is the fourth and hopefully inshallah the last lecture in session 9, which is about testing hypotheses. In the last lecture we started to develop the terminology of the framework of testing hypotheses, including null hypothesis and alternative hypothesis. So let's first start in this lecture by applying this terminology to the example that we went through last time, which is the Mendel's model. So in Mendel's model, and generally in the test of hypotheses, we have two hypotheses about the world. The null hypothesis is that the world behaves in one way, and the alternative hypothesis is that the world doesn't behave in this way, or behaves in a different way. You are given a sample of data, and the test is about deciding which of these two views, or which of these two hypotheses is supported by the data, or by the sample of the data. So the two hypotheses in Mendel's problem were, the first one was that the model is good, which was the 75% purple and 25% white, and this is called the null hypothesis. And the other one is that the model is not good, without saying why, and it's just that it is not following the distribution that Mendel suggested, and this is called the alternative hypothesis. Informally, the null hypothesis is saying that nothing is going on except chance. So if we see a variation between the sample of the sample data that we have and the population and the model, that difference or that variation is just happened by chance. Or, in other words, it's not real. It just happened by chance. The other hypothesis, which is the alternative hypothesis, is about that something else is going on. We are not saying what that thing is, but there's something else other than chance involved. Or, in other words, the difference that we see between the observed data and the model is actually real. So that's the alternative hypothesis, informally. Now, to make a decision, we have to come up with a test statistic. So the test statistic is something that we will compute from the observed data and also from the simulation that we will do. And of course, it will help us, as we saw, and we will see inshallah also in this lecture, will help us decide between the two hypotheses. So in our example, the test statistic was the absolute difference between the percentage of purples in the sample and the observed percent purple in the data. So the null hypothesis, in general, is about assuming that the sample has been generated at random under the precise assumptions about the randomness, which is the null hypothesis, and that will allow us to make simulation. It will allow us to calculate chances involving the test statistic. So the simulation will predict values for the test statistic. From these predicted values we have the distribution, and then we can compare it with the statistic value, the test statistic value that is computed from the data. So informally, the difference in the null hypothesis, the difference is due to chance. What is the difference? So the statement here says the difference is due to chance. Okay, so there are two main words here, difference and due to chance, or chance. So what is the difference? Which difference here? The difference is between the observed value of the test statistic and the predicted values that we see from the simulation, or the distribution of the predicted values. Where is the chance? Where does the chance come in? The chance comes in from the null hypothesis, from the assumptions about the model in the null hypothesis. Okay, so we assume always that in the null hypothesis there is a random process. So there is randomness somewhere. So that's where the chance comes from. The statistic, when it is computed under the null, we assume that the null hypothesis is true, and we simulate getting samples from the under the null hypothesis From each sample we compute a statistic value and we have the distribution. So under this assumption we calculate the probability distribution, actually the empirical distribution of the test statistic. And we compare it with the observed statistic. As we see here, the observed statistic is 0.013, and this is now compared with the empirical distribution. So the conclusion, if we look at the comparison here, we see that the observed value is almost at the heart of the distribution, of the empirical distribution. So it seems that the data supports the model. Okay, so the data and the model, or the data and the hypothesis, are consistent. So generally, to make a conclusion, if the observed test statistic is inconsistent, then the data are inconsistent with the null hypothesis, and in this case we reject the null hypothesis. If the observed test statistic is consistent with the null hypothesis, then we cannot reject the null hypothesis, which means that we accept it, and in this case the data support the null hypothesis better than they support the alternative. In our example, of course, it is very clear by any reasonable definition of consistency, it is very clear that the observed value is consistent with the predicted values. So we will conclude that the data supports the null better than the alternative, which means that the model suggested by Mendel looks good by this test. Of course, as we said in the last lecture, inconsistency is subjective. Someone can say this is consistent, other can say this is inconsistent. So we have two conventions. So usually we say inconsistent if the test statistic is lying in the tail of the null distribution. So we have two conventions for the tail. If the area of the tail is less than 5%, we say that the result is statistically significant. And if it's another convention is that if the area of the tail, which we called it last lecture, the tail probability, is less than 1%, then we can say that the result is highly statistically significant. Just to give you a quick idea about where do these conventions come from, they came from Sir Ronald Fisher, statistician, who has contributed a lot to this kind of hypothesis testing. He said in one of his papers, it is convenient to take this point, which is 5%, as a limit in judging whether a deviation is to be considered significant or not. So he's saying convenient. So that was the cutoff, 5% cutoff was just a convenient point for him to take. So it is clear from his words that this is subjective. In another paper, he said also, if 1 in 20 doesn't seem high enough odds, 1 in 20 of course means 5%. So if 5% doesn't seem high enough odds, we may, if we prefer it, draw the line at 1 in 50, which means 2%, or 1 in 100, which means 1% in this case. So he is saying that, to me, 5% is okay, but if you prefer, so it's very clear that it is subjective, if you prefer, you can draw the line at 2% or 1%. Personally, that's quoting him now, personally, the author, Sir Fisher, prefers to set a low standard of significance at 5% sorry, at 5% point. So it is very clear, it is subjective, and from his words it's very clear, but nonetheless, the entire universe, entire world is taking, he just ignored all of these words and took 5% and 1% as conventions. So now let's see if it is always clear that the data and the model are consistent or inconsistent, and when can we be uncertain and what should we do in this case. So let's look at another example, which is the GSIs and student problem. So what is this problem? We have a large class. Actually, in this case, it was a statistics class. The large class is divided into 12 groups or 12 discussion sections. Each section is led by like a TA. It's called graduate student instructors. Okay, so each group is led by one GSI, like one TA. And after the midterm, after the grades were released, students in specific section, it was here in section 3, noticed that the average score of their section is lower than the others. Of course, it happens all the time. But if you are in this section, then you might think that there might be a problem with the GSI teaching. So that was the stance of the students. Now, of course, especially since this class was statistics, the GSIs defended themselves. They said that, okay, so it was not because of the teaching, it was just by chance. So the null hypothesis here is that if we picked any section at random from the entire class, we could have got the average like this, like section 3. So the GSIs are just saying that it happened by chance. If you took a sample of, let's say, the section 3 class, section 3 group has 20 students. If we took 20 students out of the entire class, maybe the entire class is, let's say, 300. If you took 20 out of 300 and you computed the average of them, it will be not different from the average that section 3 got. So that's the null hypothesis, and it is clearly a chance model. Okay, because it's saying that sampling randomly from the entire population, which is the entire class now, will give us an average like this. Of course, the students have the alternative, which is that no, the average score is too low and randomness is or might not be the only reason for the low scores. Of course, you might like one of these two hypotheses, but let's see what the data and the statistics will tell us. So we'll do the hypothesis testing now on this example and see whether the data supports the GSI's position, which is the null hypothesis, or the student's position, which is the alternative hypothesis. So let's go through the code now. Okay, so we start with the data. So we have in the data, each row here is one student, the section number, and the grade or the score that he or she got in the midterm. So the scores here is from 0 to 25. So we have here like 360 or 359 students in the entire class. Now let's look at the averages. So if we group by section and computed the average, we will get something like that. So this is the actual average scores for each section or for each group. And if you look at the numbers here, it is very clear that this section has the lowest value, and it might look odd compared to the other sections. So the other sections are almost all are above 15 as a score, as an average. Maybe this one is not, but section 3 is 13.66. So that's why students have a point here. Okay, so how will we do the test? So we have to do the simulation under the null hypothesis. So what does the null hypothesis tell us? It tells us that the average of that score just came by chance. So it means that if we take a random sample from the students, from the 359 students that we have in the class, and we computed the average, we probably will get something similar to that average. So it's clear that the test statistic that we want to compute is the average. Now, when we have a sample to compute the test statistic, of course, the observed test statistic now will be this value, right? So if we pick the test statistic to be the average score of a sample of students, then the observed statistic value will be the value of the lowest section, which is section 3, which is here 13.67. Now, to do the simulation, we will do sampling. To do sampling, we need to know the sample size. So what should be the sample size in this case? Of course, it should be the size of section 3, right? So because we want to see if a sample of that size, of the size of that section is will give us something like this average. So we need to know. So this is how to get the observed average, which is the minimum here, the minimum of the values of the average. Now we want to know the sample size, so we want to know how many students in each group. So we'll group by the section, and we'll get the count of the students for each section. Here, the number of students in section 3 is 27, so that's actually the size of the sample. Okay, now we are ready to get one sample. So the sample here, we need to just sample from the original table. We sample a sample of size 27, of course, without replacement, because we need to get a sample of students without repetitions. Okay, so without replacement, so with replacement here is false, we get a sample, and the statistic is the average of that sample. Okay, so if we run this once, we get here 17.111. Okay, if we run it twice, same thing. Okay, 14.59, 14.18, 15.8, and so on. Okay, so we never got, at least in these 4 or 5 samples, we never got something like 13.6, but we'll see. Okay. As usual, we will generalize the function that will give us the statistic from one sample. So we put these two lines in a function. Okay, and we will call it, we'll do the sampling 50,000 times in this case. So as usual, loop for 50,000 times, and in each loop we will call random sample midterm average, which is this function. We get a value. It will give us the value of this statistic. We append it to the sample averages. Okay, so we'll run this. Takes time. So done. Now we are ready to do the test. Okay, to compare the observed value of the average, which was 13.67, with the distribution that we got from the simulation. I'm sure that you are excited to know the answer, whether we will reject the null hypothesis, which means that there's something else other than chance, probably the teaching of the GSI, or we cannot reject and we can conclude that it just happened by chance. So let's see. So this code will plot the histogram, and also will plot the dot for the observed averaging. The observed average of the sample that we have of section 3. So ready? Here is the distribution and the observed value. Okay, let's try to understand what's going on here. So that's the test statistic, that's the sampled averages, right? So these are the predicted values of the average score of a sample of size 27 from the class students, based on their, of course, scores in the midterm exam. So this is the observed value. Okay, it doesn't seem very obvious that this is very likely, right? So it's not at the heart of the distribution. It's not among the most common values of the test statistic, the most common values of the average. Okay, so it seems like the most common values of the average is like maybe 15 point something. Okay, and that's what we saw when we do the averages for all the sections. But still, this value is probable. It happened. Okay, now it's not very easy to decide whether this is consistent or inconsistent. As we said, it's a matter of judgment. It's very subjective. So let's see. Let's compare that with the conventions that we have. So to compute, to compare it with the conventions, we have to compute the tail probability, right? The area of the tail. So where's the tail here? Is it in that direction or in that direction? How can we know? So as we said earlier, I think in the previous lecture, the tail is in the direction that favors or that supports the alternative. Okay, so which direction here supports the alternative? The average in this direction increases. So if the average increases, then this is supporting the null hypothesis, right? Right? But if the average decreases, okay, then it favors the alternative. So that's as the average, as the value of the average decrease, that means that we are going towards the alternative, right? So the tail, if the observed value is here, okay, in this area, that will support the alternative. As the observed value, as the test statistic value decreases, that supports the alternative. Okay? So the tail is in this direction. So how can we compute now the tail area? We want to compute what is the chance, what is the probability that the predicted value of the test statistic is equal to the observed statistic value or below, or in the direction, or further in the direction of the alternative, which is the small values here. Okay? So we want to compute the area of the probability of this, the tail probability in this area. Okay, the total area here. How can we do that? We, as we did last time, we get the number of samples in this area, okay, divided by the number of repetitions, which is 50,000. Okay, so the number of samples for which the average is less than or equal to the observed average over 50,000, this value is 0.056. Okay, this value is 0.056. We call this value, so last time we called it the tail probability, okay, or the tail area. Formally, this value is called the p-value. The p-value, okay? So the p-value is the chance or the probability that the predicted values of the test statistic is equal to or further in the direction that supports the alternative to compute the observed test statistic. So in this case, the p-value is 0.05, which is clearly above the 5% cutoff, the conventional 5% cutoff. So if we will use the 5% cutoff, then what should be the decision? So the decision should be, since the p-value is greater than 5%, then we cannot reject the null hypothesis, and we conclude that the data supports the null hypothesis, or the data supports the random model, which means that we will accept the GSI's stance, and it seems we will conclude that it just happened by chance. If we will go with the convention and this data point, this observed value, is further to the left and it is beyond the 5% cutoff, then we would have concluded that the student position is supported. We would have concluded that we will reject the null hypothesis, and in that case we would say that the data is not supported by the random model. So let's now think about where exactly we can do this switch, assuming that the cutoff is 5%. Where can we switch from concluding that we can't reject the null hypothesis and that the data is consistent with the model, and switch to the inconsistency position? Where? So if we go with the 5% cutoff, then it will be the value of the test statistic that will give us an area of the tail to be 5%. How can we do that? We do that this way. We sort the values and take the top 5% and get the value at the top 5%. So I will leave that for you to look at. But if we do that, then we get 13.59. So what is this value? This value is at 5% cutoff, which means that if we have an observed value that is higher than this value, which means in this case to the right of this value, then we will not reject the null hypothesis. That means that the data and the model are consistent. But if it's lower than this, we will say that it is inconsistent. Okay, so this is like the cutoff value. What was the observed average? The observed average was 13.6. It's not very far, by the way, from 13.59. Remember, the observed average was 13.67. That one, the threshold, is 13.59. We are not very far. But by the 5% cutoff, we cannot say that the result is consistent, is significant. We can just say that the model and the data are consistent, or in other words, the data supports the model. Just for illustration, I will show you now this threshold. So I drew this line exactly at 13.59, which is the 5% point. Okay, and you can see clearly here, if we zoom in, we can see that our observed point is just before the line, the cutoff point. Okay, so if we use that cutoff point, then we can say that the data and the model are consistent. If that point were here or anywhere to the left of the yellow line, we would have concluded that the data and the model were inconsistent, and we would have supported the student's stance. So let's put that terminology in a formal way, and we get back to the slides now. So what we did here is called statistical significance. Just reminding you that we are talking about inconsistency with the null hypothesis. In doing that, we are looking at the tail, and we have two conventions, the 5% convention, and if the area of the tail is less than 5%, we say that the result is statistically significant. If it's less than 1%, we say that the result is highly statistically significant. The 5% and 1% are called significance levels. Okay, so if I used 5% cutoff, so I can say that the significance level of the test is 5%. If I used 1%, then the significance level of the test is 1%. So that's the the cutoff value that I will compare with. As we said, these are two conventions. You can have your own convention, maybe 6%, maybe 7%. Okay, but in all cases, when you do the test, you have to report the observed statistic value, and you have to report the p-value. Remember, the p-value is the area of the tail at or below or further in the direction of the alternative with the observed value. So you have to report the significance level, you have to report the p-value, you have to report the observed statistic, and you have to show the distribution, the empirical distribution. So the p-value, as we said, it is an area. Okay, it is the area below or above, even in case of the direction of the alternative hypothesis. In our case, the direction of the alternative hypothesis is in this direction, because the students are saying the average is low, right? So low values will support the alternative, so the p-value should be computed to the left. Okay, and the p-value is a chance, and of course this is equivalent to the area of the distribution of the histogram below this value. Okay, so this is informally. So p-value is an area. Formally, the p-value is called, the formal name of the p-value is called observed significance level. Okay, of course this is too long, so in short we say p-value. Type. Remember in the previous, I think, 1 or 2 slides, we said we have significance level. So the significance level is set to be the threshold, okay, in advance. But the p-value is the observed significance level, is the observed value, observed probability of the tail, the area of the tail. Okay, so that's why it's called observed significance level. So the p-value formally is defined as the chance or the probability under the null hypothesis that the test statistic is equal to the value that was observed in the data, which is observed statistic, or is even further in the direction of the alternative hypothesis. That's the formal definition of the p-value. So for each observed value of the test statistic, we will have to compute the p-value. Okay, of course, in a hypothesis test, we have just one observed statistic value. We compute the p-value for it. We compare it with the significance level, which is the cutoff point that we set. Okay, in our example, we set it at 5%, and the result was not significant at that level. Of course, if we set it at 1%, it will also be non-significant since it's not with the 5% cutoff. Okay, let's apply that quickly on the examples, on the 3 examples that we saw before. In the jury selection, the null was that the panel was drawn at random, and the alternative was that there were too few black men. The test statistic was the number of black men in the panel. So small values of the test statistic support the alternative. The alternative was saying that the black men, the number of black men is small. That was the stance of Swain. So if we look at the distribution, then the p-value will be the area to the left. Remember here, small values of the statistic support the alternative. That's the direction of the alternative. So that's the direction of the alternative. So when we compute the observed value, we compute the p-value as the area to the left of that value, which in this case, of course, it's very close to 0, which means that the test will favor the alternative. In Mendel's model, the null hypothesis was that we have 75% of being purple. The alternative was that this model is not good. The statistic was the distance in between the purple percentage in the sample with 75%, which means that large value of that statistic will support the alternative, because we will be very far from 75. So if we look at the distribution, large values means to the right. So whenever we have an observed value of the statistic, the p-value will be the area to the right here, in this case, of the observed value. In this case, the area was bigger than 50%, and by any convention, this means that we will favor the null hypothesis. It is bigger than any of the cutoff, the conventional cutoffs. And it's very clear it is consistent. For the GSI's defense that we just explored, the null hypothesis was that the scores were randomly selected, was random sample or randomly drawn from the population of the students. The alternative was that the average is too low. The statistic that we used was the average of the section of the sample. So small values will support the alternative because the students, the alternative is the student's stance, which is that the average is too low. So small values is supporting the alternative. So that's the direction for computing the p-value. So when we have the distribution like that, then small values will be in the direction of the alternative. Then when we have the observed value, the area to the left now of the observed value is the p-value. Okay? So in this case, the area was about 5.6%, and that means that we will favor, or the test favors the null if you are strict about the 5% cutoff. So if our reference point is the 5% cutoff, the 5% significance level, then the test favors the null hypothesis. Okay? Now, let's talk about if we can make wrong decisions in hypothesis testing. So the question is, can the conclusion that we make based on the hypothesis testing be wrong? Can we make wrong decisions? Can we favor one alternative while the other is actually true, and that alternative that we supported, that we favored, is actually false? Can that happen? The answer is clearly yes, it can happen. Okay, and let's see here how or when. So let's say that this is the reality. So we have two cases of the reality. The null is true or the alternative is true. And here is the outcome of the possible outcomes of the test. We might favor the null or we might favor the alternative. We have two cases in which we are okay. We are making the right decision. If the null is actually true and we favor the null, then we are okay. If the alternative is true and we favor the alternative, then we are also okay. We are making the right decision. But if the null is true and we favor the alternative, then we are making a wrong decision. That's an error. Similarly, if the alternative is true but the test favored the null, then also this is wrong decision. This one is out of the scope of the course. Let's check when we can have this case. So in this case, the null hypothesis is true, but we favor the alternative. Let's see how or when we can do that. When can we make a decision that we will favor the alternative while it actually the null hypothesis is true? How can we think about that? Let's get back to the significance level. Let's say that our significance level is 5% and it is set at that straight line, the yellow line. Okay? So if the observed value came beyond that line, below that line, okay, then we will say the test will favor the alternative hypothesis, right? When can that happen? All of these values. What is the probability that this can happen? It's actually the area, the p-value of the observed statistic. So if the observed statistic is here, then the area below it is the probability that it can happen if the null hypothesis is true. Remember, if the observed value is here, okay, that doesn't mean that it is not probable. We might say it's unlikely to happen, but it can happen. What is the chance that it can happen? It's the empirical probability at that point. Right? So, if the null hypothesis is true, but our observed statistic value is in this area, then we are making a mistake. We are making a wrong decision. What is the probability of that wrong decision? It's the probability of all values in this area. All values, the probability that the observed statistic can be in this area. What is the probability that the observed value will be in this area? It is the significance level actually. Okay, so if we use a 5% cutoff, then it is a 5% chance that the null hypothesis is true, but we actually reject it. Because it can happen 5% of the time that these values can be predicted from the population, from the model. The fact that we said 5% is not too much and it's small, okay, that's how we made, how we said that it is inconsistent, the data and the model are inconsistent, but still that can be a mistake, that can be wrong, right? Because as we see here, it is clear from the empirical distribution that we can get some values here. Right? So if the observed statistic happen to be one of these values, it is probable, but still the test will conclude that we will favor the alternative, although it might actually true that the null hypothesis is true. Okay, so the error probability, the probability that we make an error here, is the cutoff point that we are taking. If we are taking 5% cutoff, then the error probability is 5%. If we are taking 1% cutoff, then the error probability is 1%. Okay, so that's why actually in some cases, like in medical cases, when they try a new medication, they set most of the time, they set the significance level to be, what do you think, 1% or 5%? To be 1% actually, to decrease as much as we can the probability of making wrong decisions. So the error probability is actually the cutoff value for the p-value, which is what we call the significance level. So if your cutoff is 5% and the null hypothesis happens to be true, then there is about 5% chance that your test will reject the null hypothesis, which means that we made an error. So quickly, a comparison between the p-value cutoff and the p-value. The p-value cutoff, which is what we call significance level also, it doesn't depend on the observed data or simulation. This is a cutoff point that we will compare with. It's not computed from the observed data at all, and even not computed from the samples, the simulated samples. It doesn't depend on any of them. It is actually set before seeing the results, before doing the experiment, before doing the test. And the conversion values are at 5% and 1%. And that's the probability of hypothesis testing making an error. While the p-value depends on the observed data and the simulation. We compute the p-value as the area in the empirical distribution at or further in the direction of the alternative to with respect to the observed data, observed statistic. So it is the probability under the null hypothesis that the test statistic is the observed value or further towards the alternative. That's the difference between the p-value cutoff, significance level or the error probability, and the p-value. With that, we will conclude this session. Inshallah, see you in next lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.